basically performed the last operational flight under the U.S. military. Now, the Spanish Navy will probably fly the Harrier for another until the year 2030, but for the United States, yesterday, in fact, at Cherry Point, North Carolina, they basically closed the Harrier service. So yesterday was a very historic day because that aircraft has been flying for more than 40 years here in the United States on the Marine, under the U.S. Marine Corps.
Let me just make it perfect. That's the ADB occurred too, 85 or 84.
Right.
It actually became operational with the UK, I think, 69.
Yes, the aircraft, it's only for the U.S. Again, I'm talking U.S. only. The Harrier has been in service since the late 60s in the UK. But the bottom line is that that's it. Once that aircraft was gone, we were wondering what are we going to do next? And the F-35 Bravo is what came next. And that's what I'm going to be talking about. Again, and if you look at why VTOL is so hard, especially the supersonic VTOL, if you look at this slide, there's the Harrier on the left, 20,000 pounds of thrust, which is more than the F-104. It only has 15,000 pounds of thrust, but the Harrier can only go to 0.85 Mach, and the F-104 can go to Mach 2.0. So as you can see, the F-104 can easily do supersonic flight, with only 15,000 pounds, while the Harrier with 20,000 pounds can only do 0.85. That shows right there how hard it is to take off vertically, land vertically, and at the same time go supersonic. In fact, if you look at this slide, there were many aircraft that flew supersonic but never reached any production level of any kind because it's just difficult. You gotta give up so much. You gotta give up fuel, you gotta give up payload, you gotta give up armaments, whatever. It's just very hard. Until the F-35, even the Harrier, I guess, that was not possible. Now, the Russians made a great attempt on the Jak-141, but it was not enough. The aircraft, they only built about 3 aircraft, basically was canceled with the solution of the Soviet Union. But still, it was probably the best attempt by any country to do supersonic flight and at the same time vertical takeoff and vertical landing. So we need to give the Russians a little bit of credit for that. Now, when Lockheed Martin, when the government came to Lockheed, they said, well, not only do I want supersonic flight and I want vertical flight, I want the aircraft to be common among the 3 services: the Air Force, the Navy, and the Air Force, Navy, and Marine Corps. Anyway, so here we are. So they were challenged even more to be able to do that, and that it made the work of the Joint Strike Fighter even harder. And again, I can talk for hours behind the background, behind all this, but in order for me to talk about the propulsion aspects of the aircraft, I need to keep going here. Now, when it comes to turbine engines, you can either have thrust, for cruise, a high, in this case, the F-22 was Super Cruise, or you can have a turboshaft in order for you to transmit that power, that shaft horsepower to the front so that you can rotate the rotors, right? You cannot have both together. It's very hard to combine them both. In fact, until the F-35B, you never needed to combine them both. So there you go. There's a picture that shows the same thing that I just said. In a turbojet, you get 2 stages of the turbine in the back, and then you get a lot of thrust out of the back, right? In a turboshaft, you add another turbine stage, and then you move that power to the front so that you can turn the rotor of a helicopter. That's what a turboshaft is all about. So you can either have that or the other, but you cannot have it both, okay? Let me skip that real quick. Now, if you look at an engine, a turbojet engine, for example, and you look at the energy content of the flow as it goes through the engine, the compressor will raise the power, the pressure. Then you add fuel, and then that fuel, that energy, the fuel burning in the combustor going out the back, will basically drop when it goes through the turbine, okay? And then it will exhaust through the nozzle, and everything else is wasted as heat, okay? Yep. But that energy content, as it goes through the flow, you can, as an engineer, you might think, I wish I could go ahead and extract some of that wasted energy. When I say wasted, it's not totally wasted, but extract some of it so that I can send it forward, so that I can go ahead and put a lift fan in the front and be able to have a turboshaft and an engine, a turbojet engine at the same time. And that was the elegant solution that the JSF team came with to be able to combine both a turboshaft and a turbojet engine. And this is another picture of the same thing. I don't want to go into the math of it, but the bottom line is you got energy flowing through the engine, and you have pressure increases, leveling off, and also decreasing when it goes to the turbine. If you open the nozzle up a little bit, and this is the elegant solution that the JSF team came with. When you open the nozzle in the back, the pressure across the turbine has to increase some, okay? And because that increase in pressure through the turbine, you can take some of that energy and send it forward. Of course, you're gonna lose a little bit of thrust from the back, but at least you get some energy extracted from the turbine that you can send to the front for the lift fan. Okay, let me show you another slide. Oh, and by the way, that's a picture that I just mentioned, right? The thrust goes down a little bit. You see that arrow becoming a little bit smaller. The thrust becomes a little bit smaller when you open up the back, okay? But then you accelerate the turbine in doing so because you got more pressure going through the turbine, and that extra energy is what you need to put in the front, okay? And I'm not going to talk about the turbine map, but the bottom line is that what you're doing is you're moving the efficiency of the turbine from the cruise condition to the vertical takeoff condition, because you're taking energy from the floor and moving it to the front, and you're moving the design point, basically the cruise point, the design point, you're moving it away from the ideal in the turbine map just for a short time until you get airborne, and then you go cruise, and then you bring back the cruise point back to where it's supposed to be. That is the underlying performance aspects of that turbine, okay? And here it is. Again, the same graph that I showed earlier, showing how you see that green line next to the blue line, that's what, when you open up the back, you open up the nozzle in the back, the pressure drop across the turbine in the back increases. And then you can send that power, you hear my laser here, you can send the increasing pressure across the turbine, you can send it forward to the lift fan so that you can get that thrust that you need in the front. Because remember, for VTOL flight, you need to balance the front and the back, right? So you need power from the back and you need power from the front to be able to keep the aircraft level when you're taking off vertically, okay? And that is the genius and the elegance of the solution of the Joint Strike Fighter, the F-35, okay? I know you probably have some questions about all this that I did very quickly, but we can talk about that at the end. Here's the common solution too that Lockheed was told that they want, that the military wanted, right? You want an engine that can be used for normal aircraft, conventional aircraft, but you also want the same aircraft to be a VTOL aircraft. And here's the same airframe with the lift fan for VTOL, and here's the conventional aircraft where when you take the lift fan out of the way, you can put fuel in there, right? Or avionics or whatever, okay? To be able to have the same aircraft on two completely different missions. That's why the aircraft is a multi-role aircraft, okay? And here's the same thing, and you can see the thrust coming out of the back and the thrust coming out of the front, and a little bit of thrust on the side so you can keep the aircraft balanced. And that's the solution that Lockheed Martin came about, and that's why they won over Boeing on that contract. Okay, it was a very elegant and quick solution. When you see that in red, in the label in red, are the common aspects of the engine between the two aircraft, the conventional and the vertical flight aircraft. As you can see, the vertical flight aircraft has a little bit more complexity because you have roll posts, you have the lift fan, you have the drive shaft, and you have a 3-bearing swivel nozzle that basically tilts down to be able to get the back thrust that you need to go up. Okay? The conventional aircraft doesn't have that, but at least you can share the core of the engine. You see, you can share all that, you can share all that, and you can share the inlets also. Okay? So that's also very important. You save money by combining stuff from different aircraft. And the inlets, I'm not going to go about that, that's another lecture in itself. But it's another elegant solution that Lockheed Martin came about. My friend Tom Sylvester came up with that solution of using boundary layer plates, like an Air Force Phantom, And it went from all this, which is very draggy, by the way, to something that is very conformal. Let's call that divertless inlet, and that was a very elegant solution. In fact, the Chinese copied that. If you look at their latest aircraft, you'll see that they have the same inlet. They stole it, basically, from Lockheed Martin. And I don't mind saying that because it's obvious that they did that. It's perfect. It's a beautiful solution. And here are the different parts of the engine that the JSF, or the vertical flight aircraft, had. I don't want to go into that because I'm going to be going through them one by one. One important aspect, don't look at this slide, but one important aspect of the Joint Strike Fighter, when you take off vertically, it's not just a simple issue of just balancing the exhaust and the lift and all that. It's also the software and the engine fed and the aircraft avionics to be able to combine that into a propulsion system without the software so that the pilot doesn't have to think about what he's doing anymore. That's very important. Without it, the Joint Strike Fighter wouldn't have been successful either. So let's not ignore the fact that you need that. These are the different tilt angles that you do and the actual movements of the nozzles and everything else. Again, I don't have time to go into it, but I can later. Now, the three bearing swivel nozzle, that's a very good solution. Some people think that we copied that from the Russians. Maybe so. The Yak 141 had that type of nozzle. The Germans also tested it in the 1960s. But the bottom line is that Lockheed had, and Rolls-Royce both, had to do a lot of thinking to be able to make it work. And not only to make it work, but also to make it durable so that it would last throughout the life of the aircraft. Okay? Here it is. It has three bearings, and these bearings are basically motors that move the three sections of the three bearing swivel nozzle so that you can rotate it down so that you can actually take off vertically from the back. Okay? That's very important. I remember being in West Palm Beach testing this three bearing swivel nozzle. There was always a problem with the motor, there was always a problem with leaks, there was always a problem with the liners, you name it. I was always tinkering with the three bearing swivel nozzle until we finally got it right. But we got it right, and it's working fantastically in the fleet right now, and it's one of the important aspects, enablers of this aircraft. This is just telling you that when you tilt the nozzle down, there's some bend losses that you have to worry about, but then again, I don't have time to go into the theory of that. Another thing that the F-35B has to do is that it has to make sure that the nozzle in the back is a little bit shorter than the conventional aircraft. So the nozzle, even though it's common in the vertical flight aircraft, is a little bit smaller because when you're doing a short takeoff, you don't want that nozzle to be scraping the runway, right? It's tilted down when you're doing a short takeoff. So you want to make sure that it's a little bit shorter so that the nozzle in the back doesn't scrape the ground when it's taking off. Okay, that's another thing that you have to think about when you design this aircraft. The lift fan. Let's talk about the lift fan. Oh, by the way, again, thrust plate. Thrust plate is one of those buzzwords that the people that work on the F-35 use all the time. It's basically the distribution of lift between the back and the front, and that's what controls the aircraft, in pitching attitude, basically. That's a very important aspect of the design that the software has to deal with so that the pilot doesn't have to think about it, okay? It's a very friendly, user-friendly aircraft, not like the Harrier. In the Harrier program, they have to select the best pilots to be able to fly the aircraft. In the F-35B, anybody can fly. I remember flying the simulator at Lockheed Martin on the F-35, and I've never flown the F-35 Bravo ever in my life, and I was able to land it on the ship without any problem. On the simulator, obviously, but it showed me the fact that you can learn and you can be a good pilot on the aircraft. Lift fan, two-stage rotating fan. The clutch is engaged so that you can get the fan to rotate and to be able to get that lift. You get about 20,000 pounds of thrust. It's almost like a single engine on a Boeing 737. If you flew in from, let's say, Philadelphia on a Boeing 737, one of those engines that were flying you here is the same thrust as the lift fan. So you can imagine how much thrust that thing has. I remember in West Palm Beach, I used to get underneath the aircraft, the engine, when we were testing it here in West Palm Beach. We had it on 20 feet high off above the ground, and I used to get down below the lift fan when the engine was at ground idle, okay? And I was basically going like this, I couldn't stay standing normally because the force coming down from that lift fan was incredible. So I got that experience. It was very very exciting to do that. There's a cross section of the lift fan. Again, I don't have time to go into it, too much stuff here. We spend a lot of time trying to figure out the auxiliary inlet for the engine, because at low speed you need to have more air coming into the engine. And also how to design the doors that open up so that you can get air into the lift fan. We ended up testing here at West Palm Beach. Here's the test. I was here for that testing, by the way. We had to figure out how to make sure that the aerodynamics coming into the lift fan were benign to the blades into the fan. Because if you don't have good air, smooth air coming into the inlet, you can excite certain frequencies, or they call them passive frequencies, on the fan that could eventually fatigue the blades and break them. So you have to make sure that the airflow coming inside the inlet is as best as possible. You're always going to have a little bit of loss. That's what the red thing in here is for, but it's better than this, obviously. So we went from that door to this door in order to avoid all that red, which you see here minimized. See that? And there's the picture of the before and after. And there's more to it than just getting good lift, inlet recovery numbers. Okay, it's more to that, but I don't have time to go into it. Same with this. When you're flying the aircraft with the door open, there are certain joint controllability issues that you have to worry about. And this is the important flight test. This is the predicted simulated software stuff that we thought that the door was going to do to the joint moments of the aircraft. But when we tested the aircraft in Pax River, we found out that it created this curve instead of that curve. Look at how different they are. So that's the importance of flight testing, right? You never know what's going to happen until you actually test the aircraft. This is the predicted, this is the actual, okay? Okay, lift fan nozzle. Okay, beneath the lift fan, you have a variable main box nozzle that is used to kind of direct the vector of the lift fan so that you can go forward or move the aircraft back or whatever. So that's another great, great design aspect of the aircraft. And again, I could spend probably another half an hour on this alone. There's more to it, again, I don't have time to go into it. This is a great design, guys. There's so many little details that put all this aircraft together. If I had an hour and a half or 2 hours, you guys will come out of here as experts in VSTOL, okay? But unfortunately, we don't have time. There's a lot to it. Initially, on the X-35, we had a hood type of lift fan variable, nozzle on the bottom, but we changed it to a box nozzle so that we can get better stall line. You see the stall line right there? This is the hood stall line. This is the variable main box nozzle stall line, which improved. You want to get it as close as the stall point as possible to make it better, right? That's what you want, because you want an efficient box nozzle. Here's the box nozzle has vanes also, by the way, and they move according to this envelope. This is the area that you have to worry about. Depending on the regime of flight, this line, the dot, will move around this curve, depending on how those vanes are moved. And they rotate about 40 degrees per second. That's kind of quick. We move those things very quick. And the computer does all that. The pilot doesn't have to worry about it, okay? For example, in the takeoff, the pilot just put the throttle forward, and as you can see, the vanes will rotate the vector of the flow coming out of the lift fan to different angles until the aircraft is flying away. And then it goes to a vector of 50, and the door comes down a little bit, and the pilot is not even worried about any of that. It's just taking off. So those are things that the computer is doing internally when the aircraft is taking off from an aircraft carrier. The drive shaft and the clutch, very important. Why? Because you're transmitting all that power from the turbine to the front through a shaft and through a clutch, which is right there. And you have to engage the clutch. What the pilot does is he has a button on the cockpit that says stall, and he just pushes it, and the doors begin to open, the clutch begins to engage, the lift fan begins to rotate, the variable main box nozzle begins to start moving, the three-bearing swivel duct begins to come down, the airflow goes through the roll post to keep the aircraft level, and he's just sitting down and happy there without having to worry about it, okay? That's the beauty of the aircraft. Let's see, let me skip some of this stuff. I'm going to have to skip all this, unfortunately. Let me finish with this last right here. Look, the Harrier was a fantastic aircraft, okay? The F-35 is also a great aircraft. we really wanted to improve the Harrier, not just live with something like the Harrier. And that's the challenge that Lockheed Martin was given. And this slide shows you on the left some of the things you have to worry about that were not as great on the Harrier. And on the right, you can see that the F-35 was able to fix a lot of those, okay? I will go ahead and take a picture of this slide and read it on your own, so you can get a sense of where we came from and where we are today. I don't know if in the future we're going to have a replacement for the F-35B. That's for the young people in the audience to be challenged in the future. I don't know if China is going to come out with an F-35 look-alike. Maybe they are working on it right now, we don't even know it. But the bottom line is that the solutions that Lockheed Martin and the military partners, Rolls-Royce, Pratt & Whitney, and some of the other guys, which by the way, they could hear a trophy on this propulsion system, which is great. And I was very happy about that. I remember the day it was announced, I was very happy. Anyway, the fact that we were able to do all that and improve the Harrier at the same time is one of the greatest aeronautical engineering accomplishments of the last century. And I think we all, the United States industry, great credit, including members of the SAE, by the way, with their guidance and different committees that made that happen. So we should be very proud of that. And I'm done with that. Thank you very much. I think we can have